session. Today, some more different types of lattices we are going to discuss. So, one is what is a distributive lattice? A lattice is said to be distributive if for any elements a comma b comma c belongs to L, which are satisfying these two following conditions are distributive properties. So it is A, the least upper bound of A among the greatest lower bounds of BC, which is equals to this one, and A and B or C is A and B or A and C. So any lattice which is satisfying these two conditions, then that lattice is said to be distributive lattice. So here, let us consider one example. We are just taking, let us sometimes, this is one of the definition. Okay, let us, I am just taking under this definition, let us, I am considering one lattice. So A, B, C, D. This is a lattice, and this lattice, if you are considering any elements, so let us say I am taking A, comma, B, comma, C. A, comma, B, comma, C belongs to L. So what is L is equals to here? A, B, C, D. If I am taking A, B, C or any elements, then we can consider A, R, B and C. A, R, B and C. So which implies A, R, B and C. B and C, what is the greatest lower bound is A, and the right hand side, this value will become, this is the left hand side, this value, and the right hand side value is the least upper bound of A or B. The least upper bound of A or B is nothing but B, and the least upper bound of A or C is nothing but C. So now the greatest least upper bound of A or A, which is nothing but the element itself, and it is one of the property, and another one is the BC. BC, what is the greatest lower bound is A. So for this, any three elements, if I am considering, one condition is satisfied. The other condition, if I am going to take A and B or C, the upper bound, the least upper bound of B or C is D. So this is the left hand side, this value will become this. And the right hand side value is the greatest lower bound of AB. Greatest lower bound of A and B is nothing but A, or then A and C, the greatest lower bound is A, which is implies, so A and AD, what is the greatest lower bound? AD, the greatest lower bound is A, and this is also A. So for this set, if I am considering three elements, if I am taking this and it satisfies these two conditions. Suppose if I am going to consider other three elements, let us take B, C, D. I am just considering the other three elements. Let us consider B, C, D. B, C, D. So once again, if I am going to substitute here, so let us say B, R, next another one is C and D. So this is, I am going to write B, R, C and B, R, D. B, R, D. So like this. So here what is the B, and next C, D. C, D. What is the greatest lower bound is C, and next BC. What is the least upper bound is D. BD. BD, the least upper bound is D. So now this is BC, the least upper bound. BC, the least upper bound. We are considering the least upper bound is D, and this is also D. This is also D. So first condition is satisfies, and go to the second one. If I am going to replace, replace in the place of A, we are taking it as a B, in the place of B, C, and next D. So the other one will become, so this is a B and C or D, which is equals to, so B and C are B and D, B and D. So now observe this, B and CRD, CRD, which is equals to CD. So what is the least upper bound is D, and next BC, what is the greatest lower bound is A, or B and D, B and D, what is the greatest lower bound is B. So now among these two, BD, what is the greatest lower bound? BD greatest lower bound is B, and ARB, what is the least upper bound is B. Least upper bound is B. So like that, we have to consider all the any three elements. In any order, we can consider the three elements, and we have to verify whether the two conditions are hold or not, or two conditions are satisfied or not. If in any order, if you are taking the three elements, if it satisfies the two conditions, then we can say that the lattice is a distributive lattice. The lattice is a distributive lattice. So here, one drawback will be there. We have to consider all three element subsets, and we have to verify. Whether this condition is satisfied or not. Which is a tedious task. And time consuming. So for that reason, we go for the another alternate definition. Observe this. See here. A lattice is called a distributive if every element in L has at most one complement. That means every element, if I am going to consider in this lattice, it is having at most means the maximum is one complement, or otherwise it does not have any complement. Then such lattice is said to be a distributive lattice. So let us go for this. Instead of considering all the subsets, any three elements we are going to consider from L, and we are going to verify these two conditions. It will become a tedious one. It will become a difficult task. So for that, we go for this one. So here, the other alternate, that means for each and every element, suppose this is the least element and this is the greatest element. This is the least and this is the greatest element. So what we are going to say that A complement is D, and whereas D complement is A. A complement is D and D complement is A. So we can say that A and D, the least and the greatest elements are complements of each other. So A complement I am taking D, okay, and of course D complement is A. Now the remaining, what is a complement? When we say that two elements are complement, so whenever the least upper bound of those two elements must be the greatest element. What is the least upper bound of BC? Least upper bound of BC is equals to D, which is the greatest element. Now, and the greatest element and the greatest lower bound of these two elements must be equal to the least element. So what is the greatest lower bound of BC? It is nothing but A. So it is nothing but least element. So any two elements are said to be complement of each other, then the least upper bound is the greatest element and the greatest lower bound is the least element. Then we can say that, so B complement is a C, and of course C complement is B. So here in this lattice, each and every element will have a complement. So we can say that this is only one complement. So we can say that this lattice is a distributed lattice. This lattice is a distributed lattice. So in the same way, the other one, just we are going to consider, let us take A, B, C, D and E. Let us consider another lattice. So here L is consisting A, B, C, D, E elements, or 5 elements will be there. So here it is 5 elements will be. So in this we are going to find out. Of course, we can say that A complement is E and E complement is A. We are not going to concentrate we are concentrating the other elements. So now let us go for B complement. What is B complement? So now BC, I am just taking the 2 elements. BC I am going to consider. What is the least upper bound of BC is equals to E. So I can say that this is the greatest element. And the B and C, if I am going to consider, the greatest lower bound is A, which is equals to least element. So I can say that B for a complement of B is equals to C. Complement of B is equals to C. And of course, if I am going to consider another 2 elements, let us say I am taking BD. So here BRD. So BD if I am considering, first I am taking BC and now I am going to consider BD. So the second one I am considering B comma D belongs to L. Then the least upper bound of BD is equals to E. So which is nothing but the greatest element. And next B and D, which is equals to B and D. The greatest lower bound is A, which is equals to least element. So what I am going to say that B complement is equals to D. So here complement of B will have C and D. So what is the condition is L has at most 1 complement for each and every element. So here I am getting for this lattice, I am getting for the element B, I am getting 2 different complements. C and D I am getting complements. So this lattice is not distributed. This lattice is not a distributed lattice. So like that, just we have to verify any 2, 3 elements we can consider, and we have to verify this, or else this is a lengthy and tedious task. So for that reason, we are going to consider the other one. Just this definition we have to consider, and we are going to verify whether it is a distributed lattice or not. So let us consider the other example. So I am just taking A, B, C and D, E, F. So L, the lattice is consisting A, B, C and so on, F. Of course, we can say that A and F are complements of each other. A complement is F, and of course F complement is equals to A. So I am going to consider the remaining elements complements we have to concentrate. So here I am just taking B. So B and C elements I am going to consider from L. So then BRC. What is the least upper bound of BRC is E. So which is not equal to the greatest element. In the same sense, B and C, which is equals to A, which is of course it is a least element. So now I can say that B complement is not C. Now let us verify the other elements, whether any other element is having its complement. So now I am going to consider BE belongs to L. So now what I am going to get? BRE. So BE, what is the least upper bound? Is equals to F. So I can say that it is the greatest element. And what about the greatest lower bound is BE, and I am going to get A. So which is nothing but the least element. So I can say that B complement is equals to C. B complement is C. So let us, I'm just taking the another one is, of course, BD if I am considering, then the least D is not the complement of B. So this is the complement is B complement is C. Now let us go for the other point, other value. So let us consider D. So B, both are next, D, E have to consider. So D and E, if I am taking from the set L, then what about this? D or E. D or E. So what is the least upper bound? It is equals to F. So which is greatest element. And what is the D and E? D and E. So the greatest lower bound is a B, which is not equals to the least element. Which is not equals to the least element. So I can say that D complement is not equals to E. D complement is not equals to E. Then what about the D complement? D complement, whether it is exist or not. Whether exist or not. Already B complement is C will be there, and F complement is A will be there, and C complement, of course, it is A. Then D complement does not exist. D complement does not exist because these two are complements of each other, and these two are complements of each other, and these two the complement does not exist. So we can say that D does not have any complement. D does not have any complement. Okay, if it is not having any complement, no problem. So what we are saying that it is D does not have any complement. C does not have any complement. C, B does not have, D complement is not there. D complement does not exist. Does not exist. And similarly, what about E? E complement. So E complement also does not exist. E complement also does not exist. If I am taking any order, so E complement also does not exist. So here, observe all the elements. So A will have complement, F will have complement, B is a complement, and C is a B complement is C, C complement is A. Observe A, B, C, D, A, B, C, F will have only one complement, and whereas D, E does not have any complement. So, at most each and every element have at most one complement. So, we can say that the given lattice is a distributed lattice. So, in this way, we can say that the lattice is a distributed lattice or not. So, this is the another example. Now, the next other type of example is another type of lattice is complete lattice. So, the complete lattice, a lattice is said to be complete. L is said to be complete if all non-empty subsets has at least one upper bound and a greatest lower bound. That means if you are going to consider any subset of L, it has an upper bound as well as the lower bound. Least upper bound as well as the lower bound. In any way we are going to consider a subset from L, then that lattice is said to be complete lattice. Okay, so now let us say this is the example. Consider this, and then L is given, and divisibility will be the relation. We are going to show that they are going to verify whether it is a complete lattice or not. So now 1 divides all the elements, 2 divides 6, 3 divides 6. So here I am going to write at the bottom, and next 1 is dividing all the elements. Okay, so this is 3 and this is 6. So I am just connecting. So now I am going to get, this is the Hasse diagram. Obviously, we can say that this Hasse diagram is a lattice. Now we have to consider a two element. We have to consider a two elements for this. So what is here? I'm just considering L is equals to 1, 2, 3, 6. Now I am going to consider the subsets. Let us go into consider S1 is equals to 1, 2, and I am going to consider S2 is equals to 1, 2, 6, and S3 is equals to 1, 3, 6. So of course 1 divides 2 and the next 2 divides 6, and these are the possible subsets I am going to take. So now let us consider the whether it is having least upper bound and greatest lower bound. Least upper bound and the greatest lower bound. So obviously we can say that 1, 2 if I am taking, 1, 2 if I am taking, then it is having the it is having the least upper bound. 1, 2 if I am taking, what is the least upper bound is 2 and the greatest lower bound is 3. And in any order 1, 2, 6 if I am considering, 1, 2, 6 I am going to consider. Let us take 1, 2, 6, and it is having, for any pair if I am going to take, it is having a least upper bound and the greatest lower bound. And S3 in another order we are going to consider. So 1, 3 and next 6. 1, 3, 6. So for this also it is having the least upper bound and the greatest lower bound in every pair of element. Every pair of element if I am considering 1, 3, 1, 6 or anything, we can have the least upper bound and the greatest lower bound or exist for every non-empty subset. Or else if you are going to consider the other subsets also, the other subsets from this, any subsets, it will exist the least upper bound and the greatest lower bound. So we can say that this is a complete lattice. Whereas the other one, if I am going to consider, so this is, and we are going to take it as, simply we can say this, 1 is divides all the elements, and 2, 3, there is no comparison, there is no incomparable elements, 2, 3, and the next 4, 6 also divisibility relation, they are not divided, and the next of course 12 will be there. So 1, 2, 3. Next another one is 4, 6. 2 divides 4, and of course 2 divides 6, and 3 also divides 6. 4 divides 12, and 6 divides 12. So this I am going to consider it as the greatest element is 12 and the least element is 1. Now, if we are going to consider the subsets, let us take any number of subsets. I am going to consider one subset. Let us take 2, 3, 4, 6. 2, 3, 4, 6 is a subset from L. I am going to consider here. So what is that? 2, 3. Let us take 2, 3. And the next one is, I am going to consider 2, 3. There is no. So now I am considering like this. 2, 3. And the next 4, 6. Only this. So for this non-empty set, then least upper bound and the greatest lower bound, least upper bound and the greatest lower bound is does not exist. What about 2, 3? 2, 3 if I am going to consider, what about the greatest lower bound, because they are not related. And if I am taking 4, 6, what about the least upper bound? Least upper bound also does not exist. So in this way, the subsets, if I am considering all the non-empty subsets, has the least upper bound and the greatest lower bound. Of course, if I am going to consider the remaining subsets will have least upper bound and the greatest lower bound, but this subset will not have the least upper bound and the greatest lower bound. So we can say that the given lattice is not a complete lattice. Is not a complete lattice. Okay. So this is regarding the complete lattice. Complete lattice. Now let us go for the other concept. So what are the actually we can discuss these things at the beginning. These are the some properties will have. The lattice will satisfy the some of the properties. One is idempotent law, and another one is commutative property, and another one is associative property, and another one is absorption property. Absorption property. So idempotent law. If I am taking the least upper bound of the element same element a comma a is the element itself, and the greatest lower bound of a comma a is that element itself, and it satisfies. That means the finding that finding least upper bound, either any way you can consider, either AB or BA. That means it is satisfying commutative property. And next another one is while calculating the greatest lower bound, you consider in any order. So commutative property means either for finding least upper bound or the greatest lower bound, A or B or A and B, or which is equal to B or A and B and A. So both are satisfying the commutative properties. Of course, the associative also it is going to be satisfied. And then the absorption law and the absorption laws are also going to be taken care. So this is the possible A and B equals to A and A or B equals to A. So these are the properties, some of the properties which are related to the lattices, So far we discussed what is a lattice, some different types of lattices, not all the types of lattices which are related to the curriculum of our institute. So we are discussing only those things, and some of the different types of lattices and the properties of lattices that we are going to discuss on this. Now, the another concept is functions. So a function, what is a function? So here, we are going to consider A is one set and B is another set. A is a set and B is another set. Now, we are going to consider one element in A, and one element B belongs to B. Now, for each, when we say that F is a mapping from, or we can say that F is a relation from A to B. The relation is said to be function. If for each A belongs to A, there is a unique B belongs to B such that A comma B belongs to F. Then that relation is known as a function. See, here I am going to consider, let us take, I am just taking A is one set and B is one set. A is consisting, let us say, 1, 2, 3 elements, and of course B is consisting A comma B. I am just taking 1, 2, 3, A and B. A, B are the elements of B. Now, I am just saying what are the difference between the relation and a function. When the relation will become a function. Now, let us go, I am just taking 1 is related to A and 2 is related to B and 2 is related to A. If I am taking like this, so F is a relation from A to B, it is not a function because two elements are mapped, 2 is mapped to two elements, A and B, so it is not a function, it is only a relation. relation. Suppose if I am going to consider, let us I am going to take 1, 2, 3, A, B. I am going to consider like this. One is mapped to A, and 2 is mapped to B, and 3 is mapped to B. You observe this. This is a relation, and a relation here, if I am taking A belongs to A belongs to A, there is a unique B belongs to B. There is a unique B belongs to B. In such a situation, this relation is known as a function. This relation is known as a function. So here, B is called the image of A. The image of A. And next, A is called pre-image of B. Pre-image of B. So here, I am just calling A is also called, the element A is also called argument of the function, and B is equals to f of A is called the value of the function. The value of the function for that particular argument. Suppose if I am going to consider another relation, let us say this is AB, and I am just saying that, so this is a relation, and here the element 3 belongs to A, does not have any image. So this is also a not function. This is also is not a function. It is only a relation. So each and every element will have one element. Will have a unique element. If it is having more than one element will have more than one image. Then that is not a function. It is only a relation. So here we are going to consider two sets. A and B are two sets, and we are going to connect those two sets with a particular relation. And if it satisfies this condition, then that particular relation is called a function. Okay. So here we are going to take, suppose A comma B belongs to F. If you are taking, then B is equal to F of A. Also we can write, and B is the value of F of A. B is the value of A of the given function, and B we are calling it as a image. And A we are calling it as a pre-image of B. So in this way, we are going to see the difference between the relation and a function. Suppose any function f is mapping from A to B, then A is called domain, and B is called codomain. A is called domain, and B is called codomain. So this is known as a domain, and this is known as a codomain. So today I am going to conclude this, and in the next session we are going to take some problems regarding to the functions, and we have to verify whether it is a function or not. After that, what are the different types of functions we are going to discuss. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.